so please bear with me. So in the last lecture, we covered the D algorithm. We started for this example. Although Professor Virendra Singh has already covered the D algorithm, and from there he has moved to the 9-value algorithm. So we will be starting the Podum algorithm, that is next to D algorithm, for the combinational circuit. So first, let me explain the D algorithm for the same example so that we can start the next algorithm. So this was the example. If you can recall it, there was a stuck at one fold. This arrow upside means this is stuck at one fold. So as we have been discussing it, first of all, we have to activate the fault. Then we have to propagate the fault. And then there is the problem of line justification. Decision making, right? So activating the stuck at one fault means I need a 0 over there, right? So that's what A is equal to 0. Since this is NAND gate, so for NAND gate, we will apply all the other inputs as the non-controlling value. So for NAND gate and AND gate, the non-controlling value is 1. That's why all of these inputs are 0, 1. Right? Now just look at this. The actual input is 0, but the faulty value is 1. So I can represent it in this way, and this, as we have discussed earlier, this can be represented at D dash. So A is my D dash, B is 1, and C is also 1, and NAND of all of these means dash of all of these. What it is going to give me? D. So the output is expected to be D. So that's what at G I am having D value. Now how I can propagate? My job is to propagate this value at the output, and output is the AND gate, right? So let us propagate this at the output. So propagating this value to the output, there are 3 ways. What are those paths? So first path is through I gate, to K gate, or through M gate. So this is one gate, another path, and this is the last path. So if I am passing it through this gate, so look at this. If this one is 0, this A is connected to this H gate. So irrespective of whatever D value I will be having, I am having over here 1. If I want to pass this fault through I gate, it means all others are expected to be 1. All others are expected to be 1, right? So first of all, I will try to pass it through I gate. So passing through I gate means this default is there on one branch and other branch is having the small d input value. What should be the small d input value? If I want to pass this fault through this, then the d value can be 1. If this is 1 and this fault is over here, then of course here I can have d dash. And at the output of this, I can have D if all other inputs were 1. Okay. Or D can convert to, D dash can convert to D through the NAND gate only if D is ANDed with all ones or all D dash. Then only it can give you D. Otherwise, if some other branch is having, let's say 0 value or D value, then it is going to give us 0, right? So we have to make sure that other values are 1, 1, 1. That is one case. Another case, we figured out that if we are trying to make this 1, then we have to make this as 0 because this one was already 1. And if this is 0, it means I have to make this as 1. If this is 1 and another path, this is D, so definitely at K also I am having D dash. It means passing the fault along with I only is not going to work, right? So what you can do is you can make D is equal to, this D is equal to 0. So if this D is equal to 0 means it is going to give you 1 over here. It means you can pass the fault through K alone, the K gate alone. Okay. So if it is so, then we have completed that this is 1, I is also 1, J is also 1, and K is D dash. Now we have to make sure that both of these are also 1, 1. Then we will say, okay, the fault is passed through K gate alone. But making L is equal to 1 is also leading f is equal to 1, that is leading m is equal to d dash again. So basically we are having the combination at gate n. These combinations can be represented as 1, 1, 1, d dash, then again 1, and then again d. This is one combination. Another combination is 1, d dash, 1, d dash, 1, d dash. If we are taking NAND of all of these, we are getting D at the output. It means the fault can be propagated with the help of any one of the combinations. So these combinations are going to give us the input pattern 0, 1, 1. D can be 0 or 1, and then 1, 1. So these are the two test patterns. This X says that this D value A, B, C, D. This D value can be 0 or 1. So in this manner, we can have our test pattern. Fine. Now, how this decision is taken? So this is the tabular format for the value computation for the D algorithm. First of all, we will take the fault activation. So fault activation is done with the help of assigning the values of A, B, and C. So A is 0, B is 1, and C is 1. This is done because we are going to, there is something called as D frontier. D frontier means the default is passing through which gate. Those will be the D frontier. So first D frontier, we will activate the fault with the help of that. That is the D frontier gate. So the first gate is, this one is the first gate. This one is the first gate. By applying ABC is equal to 0, 1, 1, we are going to activate the fault. Okay. This is the D frontier gate. This G gate is the D frontier gate. So we are activating the fault first of all. After activating the fault, now expected to take any one fault from us. So that's why I thought, okay, let's go through I path. So I path. What are the implications? The I path. We wanted to go through the I path. So what we have done in that, the same thing we will be doing. So this ABC value to activate the fault, we have done. Then we found that G is equal to D we are having. Now we are trying that let us propagate the fault through I. So I is our D frontier. For that, I need D is equal to 1. And we are trying to propagate the fault through other value J, K, L, M. All of these are expected to be 1, 1, 1. But when I'm going to check it, I found that E is equal to 1 is going to give me K is equal to D. But I was expecting K is equal to 1. It means there is a contradiction. So it means I cannot propagate the fault along with I. Okay. So now I am saying, okay, I'm okay with this. Let me propagate the fault with I and K all together. Okay. So now the next one I will be checking that what is the E input. So the E input becomes 1 and the propagate is also A. For this, I should have the implication that L and M gates must be 1, 1. But when I am applying F is equal to 1 input, then means that is M is the D frontier. The fault is propagating through the it means that is also the contradiction. So finally, I can have F is equal to 1. That is going to give me M is equal to D. And I am propagating the fault through M. So basically, this is being through I, M altogether. So these three branches are propagating the fault altogether, and this is how my fault is being propagated. So this decision tree will come like this. First level was G, the gate which was the D frontier. The G gate was the D frontier. From G, it is going to go through or any one of these or all of or more than one of these. So I, K, and M. These are the three. Out of that, let us choose I. First decision I have taken, let us choose I. I want to pass this through I. So passing through I means I am left with the KMN. So when I am trying to pass it through N, then I am left with not satisfactory answer. My because K was D, that is contradicting K is equal to 1 value, right? So now I put K is equal to D and then I am trying to pass it to the N. So when I am trying to pass it to the N, then also it is getting filled because M is equal to D I am getting. So again I am taking M is equal to, yeah, D dash it was coming. So M is equal to D dash when I am getting, then I can pass it to N. So it means this is satisfying my test vector. So in this way, with the help of decisions, with the help of backtracing, I can have my final output of the test vector. So what we have done in this we started with the fault activation. This was the fault activation. We started with this. We found the D frontiers. So these are the D frontiers through which the fault can propagate. So these four are the D frontiers, which is I, K, M, and N. These are the D frontiers. Now I am trying one by one. Okay, let me pass it through this. So for when I backtraced and I found the other goal that these intermediate inputs should be 1, 1, 1, 1, and 1. All of these must be 1, 1, 1. If it is not so, it means I have to change my test pattern. And if I am trying to satisfy any one of these goals, 1, 1, 1, or whatever it is, it means the other intermediate values, for example, E dash, F dash, G dash, I have to set those values. So setting those values actually is forcing me to apply these intermediate values. For example, this is 1, it means E dash is 0. That was the internal branch, right? And this was the primary input. So here I am trying to have a goal by backtracing to intermediate input also. That is the problem with D algorithm. Now a modified version of that is PODEM algorithm. PODEM stands for the path oriented algorithm. So 9-value algorithm is also one of that, but I am not discussing that because that is already discussed by sir in the sequential circuits. So the algorithm remains same whether it is in sequential circuit or in combinational circuit. So there was a problem that D value, for sure, if a test is going to exist with the help of D value combinational circuit, you can find that test. But 9-value is more prominent giving the test in the sequential circuits if it is existing over there, because the D value is not able to cover the test because of the flip-flop internal state is going to change because of that. Yeah. So PODEM algorithm, we are coming to the next. PODEM algorithm, what it is path-oriented decision-making algorithm. The path really matters, how the circuit is structured, that really matters. Then we have to take the decision that through which path I want to propagate my fault, that really matters. So this is written about the PODEM algorithm. Let us understand what is written over here. So basically, fault activation and fault propagation leads to a set of line justification problems. FA is fault activation, FP is fault propagation. Fault activation we need to activate the fault. Fault propagation we need so that we can propagate that fault at the output. Okay. That creates a set of line justification problems that this line should be like the D frontier, or it must propagate the fault, what should be the other line, and like that. Intermediate node or anything, input, primary input can also be there. So that is the case of D algorithm. However, in PODEM algorithm, the value assignment is only done on PIs. Primary outputs are the only one where the value assignment is done based on the goal, right? How it is done? So it means the backtracking can only occur at the primary inputs. That is the virtue of PODEM algorithm. So it treats value Vk to be justified for line K as an objective K Vk. Vk is the value that can be 0 or 1, and K is the line that can be A, B, C, I, J, K, L, whatever it is. A backtracking processor maps the objective is K, comma 0 or 1. 0 or 1 is the value at that K value. Okay, so maps the objective into the primary assignment that is likely to contribute to achieve the objective. So basically KVK is the goal, and to achieve that objective we will directly go to the primary inputs. We will not create any intermediate, and that's what it is called as path oriented decision making algorithm. Now to understand that, let us have some example. So this is one of the example. Here the backtracing processor is explained with the help of a simple XOR gate. So this XOR gate is having AB inputs. These are the AB inputs. Now C will be equal to AB whole bar. Then D will be equal to AB whole bar plus A bar. And likewise E will be equal to AB bar plus B bar. And both of these whole bar of that will be actually your F. So finally F you will be getting A bar. So A XOR B bar, right? That's the standard XOR gate, right? Now in this we have the objective KVK. That what is KVK? Objective is F1. You have to bring F is equal to 1. Okay. So the we are not specifying that what fault is existing. We came to know that we faults only add the fanouts and input sets. So here the faults will be for these 4 lines plus these are the fanouts. These are the fault sites we have to consider. So total 8 fault sites are available. So maximum number of faults available can be 16. In this particular case, maximum number of faults available can be 16 with the help of checkpoint theorem. You can take this as an exercise, as an assignment you can take, and you can do the fault equivalence and dominance based collapsing, and you can figure out that you will be having the number of faults or less than 16 in this particular case. That verifies the checkpoint theorem discussed earlier. So now our goal is F is equal to 1. K is the F branch and Vk is K 1 value. Okay. So F is equal to 1. It means I have to set A and B. Previously, I am not aware about what A is there, what B is there. So first of all, we have to find X path from line K to the primary input. Let's say primary input is A. So X path is taken in this way. This is one way I have taken the X path. Okay. There are multiple paths for this. You can choose any one of them. What are those multiple paths? Let me explain. So this is another path. This is another path you can take. So these are the possibilities of paths. So there are total 3 paths. 1, 2, 3. Since the primary input, any one of the input you are setting at one time, so you can take any one of these paths available. It's not like that particular whatever with the red line is shown, that particular path you are going to choose. Since first thing, whatever you are going to make, you are free because there is no constraint. So you are free to choose any one of the paths. So I have taken this path, right? So after this, now we have to count the inversion parity of the path. Inversion parity is what? Whenever you find some bar of that, for example, NAND gate is one inversion, NOR gate is one inversion, right? So NAND is, here the inversion is going to happen. NOR means the inversion is going to happen. X NOR also is a similar category, and inverter also. If any one of these you are looking into your circuit, it means the inversion parity is 1. Okay. So how you have to proceed? Count the inversion parity in the path selected. You have selected one path with the red line. Now you have to count the inversion parity. So the inversion parity counting will happen from the output to that particular input. So output was F is equal to 1. This is 1 inversion parity, 2 inversion parity, and this is 3 inversion parity. So 3 inversion parities are there. Now, depending on the inversion parity, if the inversion parity is odd inversion parity means you have to take just reverse value of your goal. Your goal was F is equal to 1. The parity is the odd number of inverters. Inversion parity is odd. So you have to make the value inverted. So it means A is equal to 0 you have to set. I hope you got this point. Please type in the chat box if you are not able to understand this. Can you understand this, everyone? Okay. So basically, in power-grid algorithm, you are choosing the path. Okay. And what is that path? That path is decided by you. There are 3 paths available. Like one path is this, another path is this, and third path is you can take from this also, E to F, right? These are the 3 paths. I have taken any one of them. One path I have chosen. Okay, you are free to choose any one of the paths. So I have taken this particular path, which is shown with the red line. Now, what is the next target? My target is to count the number of inversion. So in this particular path, how many inversions are going to happen? So this is NAND gate, this is NAND gate, this is also NAND gate. So one inversion here, one inversion here, one inversion here. How many inversions are there? 3 inversions. At the end of 3 inversion, what do I need? 1. It means odd number of inverters I need. So what should be the input? The input should be 0. Instead of that, if the number of inversions were 2, for example, instead of this path, if I have chosen the path with the blue line, so in this case, how many inversions are there? This is one gate and this is another gate. Only 2 number of inversions. And what was the goal? 1. 2 inverters and goal is 1. What was the expected input? 1 only, right? I hope now you got it, right? Sai Kumar and Professor Aditya. Is it clear to you? Little bit different. Yeah, you will be having a little bit different if you are choosing other paths, right? If you are choosing the other path, the result will be different. For example, here I have shown 2 paths. One path is this and another path with the red line. So both of these paths are having the different number of inverters. Inversions. Let me say inversions. Yes, this is odd. We will be getting 0. Odd means odd number of inverters. What is see, even number of inverters means it is a buffer, right? Whether it is 2 number of inversions or 100 number of inversions, that is a buffer. It means whatever output was there, the same thing was expected at the input, right? So the odd number of inversions means it was actual inverter. So that's what the 3 or maybe 5 or maybe 7, something like that is going to happen. It means I have to change my input to whatever the goal was there. So the goal was 1. I have to change back it to 0. Okay. In the other path, if I have taken this path, I would have taken this path, blue line, then the number of inversions were 1 over here, 1 over here, 2 number of inversions. So it means whatever target I am going to put, the same target I will be having at the input. I hope you got this point now. Is it clear to everyone? You may type Y in the chat box so that we can proceed. Yeah, thank you so much. One more question. Why your target is 1? So this one target, it can be because of anything. For example, what could be possible things for this one target? So in this example, it is given to you that the target is 1. So what can be the possibilities? The possibility can be the one possibility can be, let's say this is stuck at 0. So what you are expecting at F? If F is stuck at 0, F is stuck at 0. I can represent in this way. What should be your goal? Right? So it is given in the question. I have taken one arbitrary question so that I can make you understand. Right? We will repeat the same example, whatever D example we have done, to understand how it works. Because answer we already have with the D algorithm. So when we will be repeating the same thing with the PODEM algorithm, we will figure out how convenient it is as compared to the D algorithm. Is it fine, Sai Kumar? Okay. So here we have chosen this path. So and here the inversion parity is 3. So it means I have to put 0. So this is 0 is done over here, right? Now with the help of this 0, this is 0, this was the input to this, and this was also input to this. 0 is the controlling value for AND gate and NAND gate, right? So what is the value of C and D? C and D is going to become 1, 1. Already it is set to 1, 1. You are not going to do anything, right? It is already set to 1, 1. Now we have to choose other path, right? Other path means you have to choose all paths for all primary inputs. If there are n primary inputs, then you have to choose for each one of them, you have to choose a path. So now I'm going to choose for B. So for B, what path I can choose? See, there are some X values, right? So first of all, let's say I want to choose this path. Now choosing this path is difficult because I have to target where the X value is. X means you have not set its value, right? So what are the paths left with the X value? Just have a look at that. So the path with the X value is left, X is here, X is here, and X was here. So if I am going to take it in this way, then it is not going to serve me the purpose because I have taken one constraint which was already 1, and still I am having another path. So if another path is existing, then there is no need to go with that 1 because definitely it can create some problem later on. For example, let me take this path, and this path is going to give you the same result, right? Whatever you were having in the previous case, because the number of inversions is 1, 2, and 3. So if 3 inversions are there, what we are expecting at B? Again, we are expecting 0. So both of these are 0, 0, right? So it means at D and E, I am having altogether 1, 1. 1 and 1 and dash of that. 1 dot 1 and all dash of that. What I am getting at the output? F is equal to 0. That was not my target, right? You got my point? 0 was not my target, but I am getting 0 over there, right? So what I have to do? I have to make sure that I will prefer the X path. I will prefer the X path, the value which is not assigned, the path value which is not assigned, and that is this path, X value, and then this is X value. Now I will count the number of inversions and then I will check. So target was F is equal to 1, okay. Number of inversion 1, number of inversion 2, and then I am reaching over B. So number of inversions are 2. Target is 1. What you are expecting at the input, please type in the chat box. These are the number of inversions. This is the goal. So what you are expecting? 1. Very good. Thank you so much. Yeah, Neha Singh, thank you. Dr. Aditya, Sai Kumar. Yeah, we are expecting 1 over here. So it means this value with this path, I'm getting 1 over here. So it gives me 0, 1. 0, 1 is the combination. 0, 1 if I'm targeting, what I'll be achieving. So this 1 is going to give me 1 ended with 1 is going to give me 0. 1 ended with 0 and then NAND, yes. So it's going to give me 1. Okay. So in this fashion, I can get the solution. If I would have taken, let's say, instead of taking the A and B path in this way, I have just taken A is equal to A has been decided by this path. So in that case, you can see the inversion is going to happen over here and it is going to happen over here, right? So in this particular case, this X is set to 0. Sorry, this X is set to 1. In this particular case, there are 2 inversions. So 2 inversions means same value. So the X is set to and this is also don't care. These two, I have to set B. So setting B, because this is also X, we have not set this to any value, right? And all of these are set to X values because one was the non-controlling value. So it means you can take this path. First of all, you try to cover as many as X possible. So you can take this path. Let me take a red line because number of X's will be more. In that case, X will be more. So you have taken this is equal to 1, that is leading, this was X, and of course this was also X. So the maximum number of X can be covered in this way. You can choose this. If you are choosing this, then you are having 1, 2 and 3. 3 number of inversions. 3 number of inversion means definitely we will be getting the inverted value of the goal. Goal was 1, so inverted value was 0. So 1, 0 combination, definitely that is also going to give you the goal XOR gate F is equal to 1. So in this manner, for the there is no need to assign in between. Between, like there was C, D, E. These 3 input intermediate branches were there. There is no need to assign values at all these intermediate branches because you are directly coming to the primary inputs. Fine. So we have taken again the same example we have taken, whatever example was taken in D. So what was the problem in that? The problem in that was that we were having the excheck fail over here. Our target was K is equal to 1. X path to P was failed, so we did the back tracing. So this is the objective. What was the objective? We tried to pass this. I hope this is fault activation is okay with all of you. Fault activation was, this is stuck at 1, so we have to make it 0, 1 and 1. 0, 1, 1 is the primary input set. For system, there are 3 more and we have to find out their values, right? So what will be their values for those 3 that we have to cover, and covering that value is going to give us these results. So you can go through this, you can go through this, or you can go through this. We have taken this. Okay, we have decided we will be passing through this. So what was our goal? Our goal was to make everything else to 1, 1, 1. So that was our goal. So here K is equal to 1 is one of our objective we have set because of our previous calculation. So objective is K is the branch and the value at K we are expecting 1. So this is K is equal to 1 is the target. Now from this we have to go to the primary inputs. What are the primary inputs? So primary input associated with this, which is not actually prepared, that is that was X. So the value of this was X and F was also X. And of course, this was also X. So from here, I can reach to the primary input E. and here only one inversion is there. So one inversion is there. What E I can have? One inversion. Goal was 1. Number of inversions is 1. Target is 1. So just inverted value of that I can have. So it means I will be having 0 over here, right? If I am having 0 over here, then here the number of inversions is double. So definitely J was 0. So it is creating the problem. X path check fails over here, right? So objective K is equal to 1 is going to lead the X path check fail. You got my point? How it is done? Hello? Yeah. You may type in the chat box if something is missing out. Yeah. Thank you. So already we are running a little bit late. I will try to finish it faster. So this is similar to the D algorithm tabular computation. First of all, our target is to activate the fault with the help of these 3 inputs. We have activated the fault. Then H is equal to 1 and G is equal to D. And D frontiers, this is the list of D frontiers. I, K, M, and you can say the next one is N. Now, what is the next one? You are trying to propagate it through I or K or M. Those are the D frontiers. So what is your target? Your target, let us say, PI assignment you will be targeting. So first of all, your target is what? Here your target is, this is D dash, right? What is your objective? D dash means what? Here it was D and this becomes D dash. D dash means it is 0, 1. So what is your goal? If I am making it 0, 1, what is your goal? 0, right? Goal is 0. If goal is 0, you got my point or not? D dash means it is 0, 1, right? I can have D dash at I, K or M because these are the D frontiers. This D value is passing either through this, or through this. So first of all, I am taking this as the target. So what I am targeting over here? 0, because the faulty value is 1. So my target is what? 0, right? So targeting 0, then go to the primary input. Primary input affecting this path, which is not assigned. That is what? So check the number of inversions. This is your goal. So goal is I, 0. That is your goal. Ith branch, 0 value. That is your goal. Go to the number of inversions. There is only one inversion. And then you are reaching to D. So D with one inversion, what you should have? D is equal to 1 is the assignment. I hope you got my point. Taking the path, there is only single path. There is only single path. There is no other path. That's what we have taken. D is equal to 1, right? Okay. Now the next one, D is equal to 1 is taken. And then this is going to give me I is equal to D. That is going to give me D frontiers K, M, and N. Now D can pass through these 3, right? D already passed through this, right? And D is available over here also. So what will be the set of D frontiers? Frontiers means what is there in front of D, so that I can take it to the output. So that is my D frontier, right? So if already I is having D, then my D frontier next to I is N, right? I am already over here. So next to this is N. And in front of this, I am left with this and I am left with this. So in the next case, I will be writing KMN as my D frontier. So now I have worked on these. Okay. So if I am taking, let's say directly I am taking N. N is my target, right? So N is equal to 1 is my target. Why 1 is the target? Because D dash is over here. There is one inversion. So definitely it is going to be D. So D can be written as 1, 0. 1, 0 means 1 is the true value, 0 is the faulty value. So what is the target? Target becomes N1. N1 is the target. You got my point? Because N is one of the D frontier and I am trying to pass it through N directly, skipping the M and K and MD frontiers. So I am having the target D passing through N makes it D. D dash passing through this gate should have other 111 and I will be having the target N1. Now let us calculate the other values. So D we have calculated D input. Now we are left with E and F input. What is our goal? N is equal to 1. So let us calculate N comma 1. N comma 1 we will be calculating. So how we can calculate? So it means we have to target our E and F. So let us target E and F. So targeting E through this path. There are two paths for E. We will backtrace from here, right? So you can take this as one path. How many inversions are there? Just calculate and let me know. If I am taking this path, how many inversions are there? 3. Very good. So what we are expecting at E? What we are expecting at E? 0, right? 3 inversions, goal was 1. So 3 inversions are there. Goal was 1. 3 is odd number. We are expecting 1. So what should I have at the input? 0, right? As soon as I am having 0 at the input, what it is going to give me? The 0 input over here is going to give me J is equal to 0. And this J is equal to 0, I cannot afford, right? This J is equal to 0 is making all of these as 0. 0 ended with anything. And the output is anyway 1, but that is the 1/1. 1/1 I do not need. I need 1/0, that is D, right? This is equal to 1. And this 1/0 is equal to D. Because my job is not to pass 1 alone at the output. My job is to pass D, means 1 with the error, with the fault propagated. That is my job. So it means it is going to fail. It means I cannot make it in this way. Okay. What is my next target? I can choose the path in this way. I can choose the path in this way. If I am choosing the path in this way, tell me the number of inversions. I have one inversion over here, another inversion over here, 2 number of inversions. Very good. What was the target? Target was 1. What should be the input? Input is 1 again. Thank you, Sai Kumar. So this is 1 is the input. So 1 is the input now. If this 1 is the input, how it is going to help me? Let us check it, whether I'm getting 1 over here or not. So 1 is the input. There are 2 paths, since the calculation will happen through all the paths, right? So if this is 1, this becomes 0, leading J is equal to 1. That is really good. But at the same time, this is D, ANDed with 1 is going to give me K is equal to D dash. So it means I have to choose K as one of the D frontier also. Along with N as the D frontier, I have to choose K also as the D frontier. Okay. But now at the same time, I was expecting that M and L, that path should also not create any problem. So let us keep our target same and try to fix F value. So for F value also, we will repeat the same procedure. Let us take this path. There are 2 paths. If I am going to take this path, what should be the value of F? How many inversions? 1, 2, 3. 3 number of inversions. So 3 number of inversions, target is 1. Goal is N is equal to 1. What should be the input? F is equal to 1 or 0? Odd number of inverters. Dr. Neha, it is odd number of inverters. Yeah. Sai Kumar, thank you. So it is 0, right? Inversions, odd number of inversions means it is just like inverter, right? Thank you, Dr. Neha. So 0, it means I have 0 over here. If I have 0 over here, it means F dash is 1 and 1 ended with this was also 1, right? So 1, 1 makes L is equal to 0. Then again the problem becomes this target becomes 1, but along with 1, 1. But I was targeting 1 slash 0. That creates the problem. So it means I have to choose my path again. So how I can choose my path again? I can choose my path in this way. There is another path. This is the other path. So this is 1 inversion, 2 inversion. How many number of inversions? 1 plus 1, 2. What is the target? 1. What should be the input F? So F is equal to 0. No. Even number of inversions are there. So F is equal to 1, right? Even number of inversions. Just like buffer, right? Thank you. So this is 1. So I'm going to make it to 1. So this is 1 and this is the target. So it means 1 is passed to n. Now, how it is going to create the final output? This is our final output. But here I have to check whether it is giving me the correct output now or not. So this becomes 1, this becomes 0. That creates 1 and 0 is 1. That is pretty much good. But this 1 ended with the D. This was D, right? So this again gives me D dash. So basically it means along with I have to choose K, M and N. This is the way my fault is going to propagate. You got my point? Every one of you? So this is the Podum algorithm for combinational circuits, similar to the similar algorithm can be applied to any other circuit you may have. And this is the tabular format of the same. Whatever I have discussed, the same thing is discussed over here, PI assignment. So the PI assignment, we started with the number of inversions. And then because of the number of inversions, we found some contradictory solution. X check fail, if F check fails, uh, X path check fails, then we will take the reversal and we will again take the other path. Taking the other path gives us K is equal to D. It means the K has to be taken as one of the D frontier in the decision making. Likewise, chosen first path we have chosen through L. So the number of inversions were odd. That was going to give us 0, but that was going to give us the again X check fail results. So we have chosen another path. So that is F is equal to 1. It is going to give, that is going to give us M is equal to D, and yes, of course, D dash. It is not D, it is D dash. Everywhere it is D dash. Okay. So what will be the decision tree? First of all, you are activating the fault. This is the fault activation, right? This is the fault activation. After that, see, fault activation is kind of, you can do it from the path orientation itself. Anyway, fault activation is must because the fault has to propagate at the output, then we will be targeting the goal. So let me tell you how the goal 1 is set. Okay. So first of all, this is the fault, stuck at 1. Stuck at 1 is the fault. It means just opposite of whatever fault is there, just opposite of that will come to that branch. So it means A is equal to 0. So I set A is equal to 0. Other inputs available in that immediate gate will be just the non-controlling value. A is equal to 0. Sorry. It was stuck at 1, so A is equal to 0. Other will be the non-controlling values. Non-controlling. So non-controlling for NAND gate and AND gate. What is non-controlling value for AND gate and AND gate? It is 1, right? So that's what B and C I am making 1, 1. So the combination becomes, if I am setting this to 0 and this to 1, it becomes D dash. D dash ended with 1, ended with 1, and whole dash of this. This is going to give me D. So here I am having D, right? Now this D is being propagated to the output side. So it can propagate in any one of the branches. To any one of the branches. One more inversion means here I should have D. Output should have D. So my target is output D. That's my target. You got my point? My target is output D. So now this output D means what? What is my goal? So my goal is D means the true value is 1 and faulty value is 0. So my target is n comma 1. But at the same time, I should not forget that the faulty value I should get 0. Okay, faulty value I should get 0. So by default, you can say the target is n comma D. The target is n comma D. D means the true value is 1. So depending on that true value, you are backtracking, path tracking. Remember, it is not back tracing of the intermediate inputs, but you will land to the primary inputs only. You will change the primary inputs only, not the intermediates. Directly, you will come to the primary inputs. In case of D algorithm, what we did the backward implications. For example, the n was done the backward implication, and we found that apart from this, let's say I want to pass through this, then apart from this, all others were expected to be 1, 1, 1. But we are not doing that in this case. What we are doing in this case, we are lending to the primary inputs directly. So what are the primary inputs set? If I am passing this through this, then this is already set, right? This is the implication that this D is passing through this. It means it is expected to be non-controlling. That is 1, right? So it means these are the primary inputs left over, which I need to check. Okay. In this particular case, we started with I, but the same thing can be started with M or K. In that case, you will get that this D can be 0 also. So that's what the final result becomes 0, 1, 1, X, 1, 1. That is your final test pattern. Okay, that becomes your final test pattern, and that's how the decision for this podium algorithm is going to happen. So first of all, you will determine ABC because of the fault activation. Then you are passing the fault at the output. Then you are setting the goal, and the goal is n comma 1. That goal is going to give you the decision. Make the decision is equal to 1. You change your decision. That is going to give you some value of f. You are again setting the value for f. So this f, if you are setting it to 0, then definitely you will get it fail. If you are making it 1, then you will be getting good result. So that is the PI selected to assign values in this manner. I hope you got it. So this is a little bit more about making the path oriented decision making algorithm much more uh, intelligent by the probability analysis. Yeah, so I am skipping this portion. I will be sharing these slides with you so that you can just go through these and you can just check. If some question you feel you are not able to get out of it, you can freely discuss in the upcoming lectures. Okay, so thank you so much. With this, let me finish this lecture. If you have any query, please ask. No, backtracing means you have to choose another path. Pankaj Nayak, if X path check fails, then we should go for backtracing. Yes, backtracking you have to do. You have to choose another X path. Yes, you cannot directly change it. Directly, how you can flip the bit? If the another X path also, let's say that is also having the same number of inversions. Let's say previous one was having 3 inversions, and the next one you are choosing that is also having 3 inversions. It means there is no possibility to flip the bit, right? Whatever we have discussed in all these cases, luckily we used to have 2 paths, right, where the number of inversions were differing. Means multi paths where one number of inversion we have chosen that was giving maybe odd and the other was giving even. So the bit was flipping because of that. It was not our fancy idea, Pankaj Nayak ji. it was not a path, it's path, you can choose another path. And another path finds, okay, the number of inversions are differing, it means the bit is flipping itself. We are not flipping, we do not have any right on that. Okay, it's the circuit's decision, it is the path's decision that which path we have chosen. Fine. Any other question? So if you have any other question, you can type in the chat box so that we can discuss that, and after that we will be concluding this session. I think there is no more question. So today's session already 40 minutes late we are running. So let me conclude the session. We have discussed, Sir has discussed all the things related to sequential path testing, memory testing, DFT, design for testability. Sir has also discussed the extension based testing for the sequential circuits. That is very much important because instead of taking the sequential circuit ATPG, it is reducing the number of iterations and the number of the time required to test that is reduced much. So that's what that is practiced more, because the time is really very important when we are talking about the VLSI circuits. It means we are directly connected to the market. You can see if you are purchasing a phone over here, let's say this June you have purchased a phone, next June let's say you want to buy one more phone, definitely you will feel that whatever phone I purchased last year, that is actually kind of outdated, because the lifespan is very time to market you have to keep very short. Otherwise the other competitors are beating you, and your profits are taken away by other companies. So that's what they have to reduce the time as much as possible, whether it is design, whether it is testing, whether it is validation, or whatever process it can be. So things are going in a particular system to design, there are n number of blocks. So everything, for example, we are talking about a phone or something else, so there are different blocks. For example, USB block is one thing, media block is another thing, central processing memory, and like that, right? So every block is assigned to a separate team, or maybe some of the part are outsourced, or maybe reutilized from the previous thing, and those are updated, some add-on values. If you will not update them, you will not have some add-on values, the customer is not going to pay you much more amount. You are targeting the much higher amount with the incremental changes in the features, right? So that's what our target is always in the VLSI, any of the cycle, or in any, it is not only on in VLSI, it is applicable to all the industries, whether you are designing a two-wheeler, four-wheeler, electric vehicle, battery, or something else. It is equally applicable that your time to market has to be reduced. It means your production, your testing, and related things you have to reduce drastically, right? So that feature has been explained by Professor Virendra Singh. I have discussed combinational circuit testing. Today we have discussed the PODEM algorithm. So I will be sharing one PPT with you. You can find that PPT that is related to implementation of PODEM algorithm using any of the language. So we have used MATLAB language. Mr. Sanjay Bagaria has helped me in that. So I'll be sharing that PPT. I'll request you please try to reproduce the results for the PODEM algorithm. There are some circuits given that PPT, and code is also given. So I request you to go through that and try to recreate the results over there so that you can understand how it is going to work, right? So those who are not having this MATLAB in their system, or the institute is not going to provide, they can use Octave. Octave is like the online platform. You will be using MATLAB kind of a script, and this is going to run it for you for free. Or maybe another one is the Scilab. Scilab is also a good thing, that is open source, but the Scilab has a little bit variation in the script writing at some or other places, a little bit minute differences there. So it's up to you, whatever language you want to choose. We have taken MATLAB language, script is in MATLAB. I'll be sharing the PPT. You can choose Python, C, C++, or whatever language you want, but you try to at least create the results for any one circuit using the Fordham algorithm. That is the assignment. Today by late evening, we will be plotting the quiz 1. So I request you to please submit the quiz 1 by tomorrow evening. Okay, tomorrow evening 6 p.m. you have to submit the quiz. Thank you so much for your patience and your time. Happy learning. Thank you so much. Bye. Gaurav?
Yes, ma'am.
Yes, let us stop the session now. It is already, we are 41 minutes late. Okay?
Okay, ma'am.
Okay, thank you. Thank you so much.